On number 35, it deals with damp motion, and it gives you the freak show of an equation which represents damp motion. The actual problem statement says that the distance d in meters of the bob of a pendulum of mass from its rest position at time t is given, which is that equation. Assume that the release position is to the left of the rest position and represents a negative direction. So that is important to know. Okay, so since this is the equation that's given, here's sort of the form of it, where A, the absolute value of A, is your amplitude. B is your damped motion, but B also occurs over here. We have the period, which we get from W. We have time t, which is like our variable. And we have mass, which is used a few times. Okay, so first, this type of equation will ask you to find the damping, to find the mass given like a damping factor. So you could look at two things. You could look at this, because B is your damping factor and M is your mass, so you could look at that. Or you can look at this, because B is your damping factor, M is your mass. So I'm going to choose to look at this. So let me write it. So B squared over 4M squared. Okay, so I'm told that I have a damping factor of 0.8. So that is my B. So I have 0.8 squared over 4M. And in my actual equation, that's this part right here. So this equals 0.64 over 900. So I could go ahead and solve this by cross multiplying. So this times this. But then I do know that 0.8 squared is 0.64, so I could just set the bottom equal to each other. But let's continue with cross multiplying. So I multiply these. I get 576 equals 2.56 m squared. So divide 2.56. And I get 225 equals m squared. Well, to go to the square, just square root it. So I get m equals 15. And don't worry about plus and minus on this one because it's just one direction. So because it's mass. Oh, there's my work. Okay, so I cross multiplied, and this times this got. Oh, excuse me. This times this got. Whoa. Okay, now I've cross multiplied up here, and I got 576 cross multiplied here. Got 2.56 m squared, divided by the 2.56, and got 225. Then I square rooted it to get rid of the square on m, and that found that m equals 15, and since m is mass, that's in kilograms. Okay, so that's one part. Now it asks, what is the initial displacement? And that's assuming that like time equals 0. So you can plug 0 into this nasty equation and get your initial displacement out. Or you can look at your, amplitude. So this right here is your initial displacement. Always. So your initial displacement is the absolute value of this. So it's 10. But then you do need to look at the sign of it to see whether it's going to the left or the right. In the problem statement, it said, assume that the release position is to the left of the rest position and represents a negative direction. So since this is negative, and it said that left is negative, it's going to be 10 meters to the left. So that is the initial displacement. Then it's going to want you to pick a graph of it. So you can plug this into your calculator. That's what I would recommend to do because it's going to be gross. And it will look something like, since it was negative 10, it'll be down here. And it'll be like, and it's going to get closer and closer to 0 as it goes on. The next question that it actually usually asks is what is the displacement after the first oscillation? So meaning like when it comes from here, goes up and comes back down. So if you plugged it into your calculator, just find the minimum of this and look for the y value. Lastly, it asks what happens to the displacement of the bob as time increases with bounce, so as time just goes on. Well, because it's slowly getting smaller and smaller and smaller, the displacement is going to approach 0.